Okay, our final lesson in this unit is lesson number 7. It's about particle physics. And sometimes, depending on how far we get in this course, sometimes we have time to talk about particle physics. Sometimes we don't have time to talk about particle physics. But I'm still going to present this lesson because no matter which semester you happen to take this course with me, this lesson is more of a for interest's sake kind of lesson than really a very difficult kind of number crunching lesson. As we've learned in previous science courses, our thoughts about matter and what makes us and everything around us has changed, and it's evolved quite a bit. So we know that basically our understanding of the atom significantly changed from what the Greeks thought to basically the current accepted notion that the atom is arranged into a nucleus, which has protons and neutrons, and there's electron clouds that surround the nucleus. And this lesson really is dedicated to explaining some of the current theories that explain some of the lingering questions. Okay, so we'll look at matter first, which is the standard model, and then we will look at forces and kind of talk about them in more detail. So the standard model of fundamental particles and interactions is the latest model of matter and forces. Okay, it answers questions about how the nucleus is held together, why certain elements experience nuclear decay. The model describes matter as being composed of smaller, more fundamental particles, leptons and quarks. Okay, so let's take a look at what it looks like, because here we have matter, and it's arranged into two major subcategories: quarks and leptons. The quarks are, of course, really, when we combine different quarks together, we get different hadrons. Okay, and hadrons are arranged into two different groups. There's the mesons and there's the baryons. And part of the baryons are, of course, there's two members of the baryon family are protons and neutrons. So quarks come together, they form hadrons, and depending on how those hadrons form, we either get mesons or we get baryons. Leptons, which is the other branch, exists of muons, tauons, and electrons. Okay, and when these guys form with these guys, we get atoms and molecules. Okay, so let's look at leptons first. The electron is a member of this family of particles called leptons. The particles are so basic. Leptons don't have any internal structure. That's what right now. That's the way we think about them. Originally, we used to think that, electrons had no internal structure, protons had no internal structure, neutrons had no, but we were wrong about the protons and the neutrons. So who knows what the future will hold, but it's pretty assumed that at the present time, leptons are so tiny, there's no internal structure. They are small, 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 and very basic. They have characteristics of spin, charge, and mass. All right, so the electron has a symbol E-. Its antiparticle is the positron, which is an E+. It has a mass, and you'll notice what we're using for mass: mega electron volts divided by c squared. It's just subatomic physics. This is the units that we're going to use for mass. 0.511. The charge on an electron is, of course, -1. And its spin, it's a spin 1/2 particle. So if you've taken quantum chemistry and you've looked at spin 1/2 particles, perhaps this is familiar to you. The electron, basically we can populate this chart, right? And the population of this chart, for your purposes, is not really that important. It's just to kind of know that there's a such thing as a muon, which is a mu, right? And a positive muon, right? Which is a lot heavier than an electron. And a tauon, which carries a symbol tau and has, of course, a mass that's enormous in comparison to an electron. So these are all subatomic particles. Okay, they all have spin 1/2. And you'll notice that this is the one thing that separates them from their hadron brothers and sisters. The electron, the muon, and the tauon each carry a charge of -1, and each of the electron, the muon, and the tauon have an associated neutrino. The electron neutrino, which has a mass of 0 and a charge of 0. The muon neutrino, who has a mass of 0 and a charge of 0. And the tauon neutrino, who has a mass of 0 and a charge of 0. They all, however, have spin 1/2. Okay, so one of the interesting questions is, of course, okay, well, where do we see muons and tauons? And that I'll leave to you to discover. There's some really, really interesting reading in your textbook that I would encourage you to do. So these particles are not affected by the strong nuclear force. Rather, they interact through the weak nuclear force. Right? So they're grouped into pairs. Each pair is a charged particle and a neutrino. Neutrinos have a very small rest mass, and they travel very close to the speed of light. They're nearly impossible to detect, even though billions of them are passing through us every second. In the recent past, of course, neutrinos become very popular because a small group of researchers thought that they may have discovered neutrinos that travel faster than the speed of light, although really it hasn't been duplicated. And so I think there's some thoughts that, of course, they didn't find neutrinos that traveled faster than the speed of light. But there's, of course, a minute physics video, which is right there. I play it in class. Minute physics video that you should definitely watch about faster than the speed of light neutrons. Muons and tauons. These are found in weak electromagnetic interactions. They have the same charge as an electron, but are much heavier. Right? So evidence also suggests that, of course, each lepton has an antiparticle. Antiparticles carry the same names, are equal in every way, but have the opposite charge. And so these muons and these tauons, they're found really in weak and electromagnetic interactions, and those are things that you can look for and do some reading on your own. Okay, let's talk about quarks. So we're talking about the other half of this. In 1964, M. Gell-Mann and G. Zwig proposed that all matter not classified as leptons is made up of quarks. Physicists have given very colorful names to each type of quark to help remember their interactions and their properties. So here is a little table. Again, this is really just from your textbook. So there's the up quark, the down quark, the strange quark, the charm quark, the top quark, and the bottom quark. Here's their masses, which you'll notice are in increasing order. Their symbols, the masses, of course, is given in giga-electron volts per c squared, so they're much heavier than the leptons. And the charge is not a full unit. Like electrons have a charge of -1. These are, of course, thirds of a charge. 2/3, third, and so on and so forth. There are also antiquarks, which have the same mass but opposite charge. They're not shown here, so there's an anti-up, an anti-down, an anti-strange, an anti-charm, and so on and so forth. Right? So there's all the antiquarks as well. They're not shown here. Hadrons then basically are what happens when quarks get together and make up different particles. Two types of hadrons, baryons and mesons. All baryons are made up of 3 quarks, and there's about 120 different of those. Right? Mesons consist of 1 quark and 1 antiquark. Okay? So the proton and the neutron are 2 of the 120 different baryons. Mesons, there's about 140 different ones of those. An example is the pion, which is pi plus, which is an up quark and an anti-down quark. And we can come to a little example. Calculate the total charge on a pion, which is an up and an anti-down. Well, the charge on a pion would be 2/3 of an electronic charge, because that's the charge on an up. And the charge on an anti-down would be plus 1/3. So a pion carries a charge of E. A proton, which is an up, and a down, basically carries 2/3, because that's the charge on an up, plus 2/3, because that's the charge on an up, minus 1/3, because that's the charge on a down, which tends to be E. So the charge on both is just the electronic charge, which is 1.602 times 10 to the negative 19 coulombs. And this is about as in-depth as we're going to get. There's a ton of more reading that you can do, and there's a ton of more enrichment that if we have time in class this semester, we'll take a look at. But let's talk about fundamental forces, because there's 4 fundamental forces of nature, and that's the gravitational force, the electromagnetic force, the strong nuclear, and the weak nuclear forces. All other forces we have encountered are caused by one of those 4 fundamental forces of nature. We've examined a few of them when we looked at fields, right? In terms of quantum mechanics and the Standard Model, force is thought to be carried out, though, in the process of interactions between fundamental particles and the exchange of force-carrying particles. And those are known as bosons. So bosons are force-carrying particles, constantly exchanged between masses and charges, and each of the 4 fundamental forces has an associated boson. All right, so gravity, its boson is the graviton. It has a very, very weak relative strength. The electromagnetic force-carrying particle is the photon, which has a relative strength of about 10 to the minus 2. And it carries the symbol nu, which is right here. The strong force is the gluon. Okay. Its relative strength is 1. So everything's considered and measured with respect to the strong nuclear force. It is much stronger than gravity or the weak or the electromagnetic. Okay, so and its symbol is G. And then, of course, the weak force, which either has a W negative, a W positive, or a Z naught, it has a relative strength of 10 to the minus 15. And, of course, its symbols are here. As an analogy, if you want to think about basically the way these force particles work, it's like a cloud of swarming bosons, which determines various interactions, surrounds each subatomic particle. So electrons can be considered to be surrounded by virtual photons, and that's what mediates the electromagnetic force. So it's just a very, very small analogy, but boson exchange is something that Richard Feynman developed a way to visually explain kind of the interactions between virtual particles and bosons. Okay, so what Richard Feynman did was he got there's all these different symbols. So a real particle carries a straight line, a virtual particle is a dashed line, a photon has this wavy line, a gluon has like one of these loopy lines, and so on and so forth. And so what Feynman did was he took time, put it on the y-axis, and space, and he put it on the x-axis. And so what this is showing, for example, is that this is showing that a neutron, N, and a proton, P, near. They get closer in space. And then at some time, they share a virtual pion. And then a proton and a neutron emerge. Okay, so here at position A, a neutron and a proton approach. And then at position B, at close distance, they exchange a virtual meson or a pion or whatever, whatever this symbol might be. So in this case, it's a pion, but we'll just say it's a virtual meson. And then a new proton and a new neutron recoil and kind of go in their own separate ways. Right? So this would be one type of interaction. Okay. So then here's example 2. Let's describe what's happening in this Feynman diagram. So here, of course, I've got a proton and I've got an electron, and they near each other, right? So we could say that a proton and an electron near. They have an electromagnetic interaction via the exchange of a photon, right? This wavy line. And then, of course, they recoil and they go in their own separate directions. So your homework questions, if we get there again, there's a couple questions on 276, and there's a couple questions here. I put these in here because this lesson is not always included. So if it is included this semester, this is your homework for tonight. Take a look at it. And that's all that there is to describe. There's, of course, this is like the tip of the iceberg. And there's so much more great particle physics and quantum physics and all this good stuff to talk about. But in high school, you can only do so much. So the rest of it has to wait until you are in university.